Okay, so welcome to my series of videos on statistics, and in this video, I'll be teaching on sampling distributions. So I'll be introducing you to sampling distributions. Now, this video will be in two parts. In the first part, I'll teach on sampling distributions of the mean. And in the second part, I'll teach on sampling distribution of proportions. Okay, so it will be in two parts. But before then, I would like you to like, comment, subscribe, and share. But most importantly, I would like you to subscribe. Now, first of all, let's discuss the issue of sampling error, right? Let's discuss the issue of sampling error. Now, when we talk about sampling error, what is sampling error? Now, remember that whenever we do sampling, sampling is not the entire population, okay? Whenever we do sampling, it means that we choose a proportion of the population to represent the entire population. Now, what this means is that when I compute mean for the sample, it does not mean that if I had the entire population, the mean I'll get for the entire population will be the same as the mean I had for the sample, okay? So anytime you are sampling, remember that any measure that you compute for the sample, okay, any measure, be it mean, standard deviation, differences, variances, whatever statistical measure we compute for the sample will not definitely be the same figures if we had the entire population to compute. Now, this therefore means that the difference between any measure computed for a sample, okay, and the corresponding measure computed from a population is called sampling error. All right, the difference between any measure computed for a sample and the same measure computed for the entire population is called sampling error. So it means that the difference between a sample mean and a population mean will be called the sampling error of the mean. The difference between a sample standard deviation and a population standard deviation will be called sampling error of the standard deviation. All right. So any difference between any measure computed for a sample and a corresponding measure computed for a population is called sampling error. Now, before we move on, I want you to understand some of these terms. You see, any measure computed for a population is called parameter. So if I compute the mean for a population, the mean is a parameter. If I compute the standard deviation of a population, it's also a parameter, okay? If I compute the deviations for the entire population, it's called a parameter. So any measure computed from the entire population is called a parameter. So parameter is a generic name used to represent any statistical measure computed from an entire population. On the other hand, if these measures were to be computed from a simple random sample, we will call these measures a statistic, all right? We will call these measures a statistic, okay? So what I want you to know is that any measure computed from a sample is called a statistic, all right? A statistic. So statistic is any statistical measure computed from a sample. It's called a statistic. Now, when we are talking about a sample where we compute a measure from and we call that measure a statistic, that sample must not be any kind of sample, okay? That sample should be a simple random sample, all right? A simple random sample, a sample which is in such a manner that all the population was given equal chance of being selected. So for more details on the sampling techniques, please find my other videos, which is on sampling, all right, to give you further details on sampling techniques. Now, as we learned in the video on descriptive measures, population mean is summation of all the figures from the population divided by the population, the population size. And then the sample mean is summation of all the figures from the sample divided by the sample size. So if I have a sample mean of 99.2 and I have a population mean of 98.6, the difference between this sample mean and this population mean is called the sampling error. It will be 99.2 sample mean minus population mean of 98.6, right? Now, the sampling error, or the difference between the mean of the sample and the mean of the population, which is called the sampling error, it will depend on which sample is selected, all right? So different samples may give different sample means, and it may give different sampling error figures, okay? Different samples, if I choose random samples, okay? If I choose random samples from a population, somebody's random sample, the mean will be different from my random sample, the mean, all right? So the size of the sampling error depends on which sample is selected, sorry. The sampling error may be positive or negative. So when we talk about sampling distribution, it is the distribution of all possible values of a statistics for a given sample size that has been randomly selected from a population, all right? So what it means is that if I choose different samples from a population, okay? If I choose different samples from a population and I compute mean for these different samples and I plot them on a histogram, I'll get a sampling distribution, all right? If I choose random samples from a population and I compute any measure, whether mean or whatever, but I'm sticking to mean for now. If I compute mean of all the several samples and I plot that on a histogram, I'll be able to get a sampling distribution. So it will look like this, right? It will look like this. It will look like this. Now, to understand this better, let's talk about the theories concerning sample means, which is more or less like the characteristics of a sampling distribution, okay? These theories are the characteristics of a sampling distribution. And I've told you that sampling distribution is a distribution or a graph of all sample means which have been computed from random samples selected from a population. Now let's look at the first theory. For any population, the average value of all possible sample means computed from all possible random samples of a given size from the population mean will equal, from the population, sorry, will equal the population mean, all right? So we are going to go through this for you to understand it carefully, okay? The theory says that when a given population, the average values of all possible sample means computed from all possible random samples from a given size. So the keyword is given size of the population will be equal to the population mean. So let's use figures to illustrate this. Now, let's say we have figures like 1, 2, 3, 4, and 5, okay? Remember, this is the entire population. This is the entire population, okay? So the mean is sigma x over n, which is 15 over 5, and it's 3. So this is the population mean. It means that the population mean is 3. Now, the theory says that if I choose a sample size of 2, okay, and compute the mean of all possible samples, which has a sample size of 2, and find the average of all those sample means, I'm supposed to get the population mean of 3. Let's do it. So let's say we are looking at a sample size of 2. We are going to choose all possible sample sizes of 2 from this population. All right. So if you want to know how many sample sizes how many combinations which has a sample size of 2 that we can get from this population, the population is 5, and we want to combine them 2 by 2. Okay. Each possible sample must have a sample size of 2. We're going to choose 2 figures and combine them as much as we can from this population. So you can just punch on your calculator 5 combination 2. So 5 figures, how we can combine them 2 by 2, you get 6. I'm sorry. You are going to get we are going to get 10 pairs of this, 10 pairs of this, okay? I'm going to get 10 pairs. But you see, let's use a simpler example. Once we use 5 figures, 10 pairs, the calculation will be too much. So let's assume these figures rather. Let's say we have figures like 1, 2, 3, and 4. So let's take 1, 2, 3, 4. The mean will be sigma x over n, which is 1 plus 2 plus 3 plus 4 all over 4, which is 10 over 4, and the answer is 2.5. So this is the population mean. So we are going to choose a sample size of 2. All right, let's choose a sample, all possible sample sizes of 2 from this population. So it means that 4 figures, we are going to combine them 2 by 2. So if you want to know the number we can get from this, you can just punch on your calculator 4 combination 2. I think you'll get 6. So it means that you get 6 pairs of 2 figures from this. And that will represent all possible sample sizes of 2, 2, 2 from the population of 4. Okay. So what this means is that we want to choose sample size of 2 from these 4 figures. Okay. We are going to get 6 of them. So you have 1 and 2 as a sample size. We will have 1 and 3 as a sample size of 2. We will have 1 and 4. We will have 2 and 3. We will have 2 and 4. And then we will have 3 and 4. So I want to choose 2 figures randomly from this. These are the possible outcomes, 6 of them. We want to know how I did it. I just said 4 figures, if you are combining them 2 by 2, how many pairs will we get? That is 6. You just have to punch your calculator 4 combination 2, you get 6. All right. Now let's find the mean of these figures. So the mean of these figures, so 1 plus 2 is 3. Divided by 2 is 1.5. Because mean is summation of the figures divided by the number of figures. So 1 plus 2 is 3. Divided by 2, because there are 2 figures, so 1.5. So the second one will be 1 plus 3 over 3, which will be, sorry, the figures are 2. So it will be 4 over 2, which is 2. This one will be 1 plus 4 over 2. That's 5 over 2. We will get 2.5. And then here we have 2 plus 3, which is 6 over 2. We will get 3. Sorry, 2 plus 3 is 5 over 2. You get 2.5. Sorry. And then 2 plus 4 is 6 over 2. You get 3. And then 3 plus 4 over 2, that will be 7 over 2, and that is 3.5. Okay. So these are the sample means. The sample means are 1.5, 2, 2.5, 2.5, 3, and 3.5. Now let's find the average of all the sample means. If I find the average of all the sample means, I'm going to get 1.5 plus 2 plus 2.5 plus 2.5 plus 3 plus 3.5 all over. There are 6 of them. So 1, 2, 3, 4, 5, 6, all over 6. And that will be 15 over 6 and that is 2.5. Okay. 15 divided by 6 is 2.5, which is the same as the population mean of 2.5. Okay. So that is why this theorem says that for any population, the average value of all possible sample means computed from all possible random samples of a given size from the population will be equal to the population mean. So let's do that of a sample size of 3. We are testing everything. Here we chose a sample size of 2. Let's try for the sample size of 3. If I'm choosing a sample size of 3, I should get 4 combination 3. I should get like 4 pairs. So 4 figures, I'm combining them 3 by 3. I should get like 4 pairs. So the first pair will be 1, 2, 3. The second pair will be 1, 2, 4. The third pair will be 2, 3, 4. The fourth pair will be 1, 3, 4. I think these are all the possible random these are the possible sample size of 3 I can get from those 4 figures. So here, if you add everything, 1 plus 2 plus 3 divided by 3, that will be 6 over 3, and then it is 2. The second one will be 1 plus 2 plus 4 divided by 3, which is 7 over 3, which is 2.33. The third one will be 2 plus 3 plus 4 over 3, and this will give us 9 over 3, and it is 3. The fourth one will be 1 plus 3 plus 4 over 3, and that will be 10 over 3, and that will give us 2.67. Now let's find the average of all these sample means. So the average of all these sample means will be 2 plus 2.33 plus 3 plus 2.64 all over 4, and that will be 10 over 4, and it is 2.5. And 2.5 is the same as the population mean. All right. So we have proved the first theory. We have proved the first theory. We have proved the first theory. Okay. Somebody can even try a sample size of, okay, I think we can, for 4 figures, we can only get a sample size of 2 and a sample size of 3. All right. When you use all the 4, it will be the entire population. So we have proved the first theory that for any population, the average value of all possible sample means computed from all possible random samples of a given size. So we used a given size of 2 and we used a given size of 3. We have realized that the mean or the average value of all sample means is the same as the population mean. All right. So when this happens, we say that the estimator is unbiased or the mean is unbiased. So when we say an estimator is unbiased, it's a characteristic of a certain statistics in which the average value of all possible value of the sample statistics equal to that of the parameter. So when your mean is unbiased, it means that the mean, it's a mean in which the average of all possible means, all possible sample means is equal to the population mean. Okay. So here we are proving that our mean is an unbiased estimator. The second theory says that for any given population, so for any population, the standard deviation of all possible sample means computed from all possible random sample sizes of n is equal to population standard deviation divided by the square root of sample size. And this is also called standard error. So let's also prove this. What this theory is saying is that, you see, remember, so let me write these figures down. Remember that when we were choosing a sample size of 2, okay, when we chose a sample size of 2, the sample means were 1.5, 2, 2.5, 2.5, 3, and 3.5. Remember this. And when we found the average of these sample means, we had 15/6, and the mean of the sample means was 2.5. Okay. Now, this question is the theory is also saying that if I find the standard deviation of these sample means, okay, so let's find the standard deviation of these sample means. Let's work it together. Remember, standard deviation is sigma x minus the mean, okay? Sigma x minus the mean squared, of course, divided by, so sigma x minus the mean squared divided by n, okay, divided by n, because all these figures, we don't use sum, so all of them, so that's why I've used n. Now, for this set of figures, there is everything, so that's why I used n, okay, the capital N. Now, let's find the standard deviation. It will be 1.5 minus 2.5 squared plus 2 minus 2.5 squared plus 2.5 minus 2.5 squared plus 2.5 minus 2.5 squared plus 3 minus 2.5 squared plus 3.5 minus 2.5 squared, everything over n, okay? So the n, the number of items there are 6. The number of items there are 6. The number of items there are 6. Now, if you do this correctly, you are going to get 1 plus 0.25 plus 0 plus 0 plus 0.25 plus 2.25, all divided by 6. So when you add all the numerator, you get 3.75 divided by 6. The answer is 0.791. All right. So remember that the standard deviation of all the sample means was 0.791. Now let me take you back a little. This was the population. Okay. The population was 1, 2, 3, 4. This was the population. And the population mean was 2.5. Now let's compute the population standard deviation. We should have done it earlier, but let's do it now. The population standard deviation will be 1 minus 2.5 squared plus 2 minus 2.5 squared plus 3 minus 2.5 squared plus 4 minus 2.5 squared. This was the population standard deviation all over n, okay? So it's 4 all over 4. So when you compute the population standard deviation, the numerator will give us, so the numerator will give us 5 over the denominator, which is 4, and that will be 1.25. So the variance of the population is 1.25. So if you want to find the standard deviation, you find the square root of 1.25, and that will give us 1.118 approximately. We should have done this earlier, so don't get yourself confused. So what it means is that the population mean is this 2.5, and then the population standard deviation is this. Okay, so remember, population mean is this, and population standard. So the population mean is 2.5. Population standard deviation is 1.118. Okay, let's remember that. Now let's go back to proving of the theory. Now, this figure here, as we have been following, is that we first of all computed the mean of the sample means, which is also 2.5 like the population mean. But the standard deviation of the sample means here, first of all, this is their variance. all right? Remember, this is their variance. Okay, this is their variance. So their standard deviation will be equal to square root of 0.791, and that would be 0.889. Okay, there is the standard deviation of the samples, all right, of the sample means. Standard deviation of the sample means. Now, the theory says that the standard deviation of a sample means, this figure, should be equal to so let's go back, let's look at it. For any population, the standard deviation of all possible sample means, which we have done, computed from all possible random sizes of n, is equal to the population standard deviation divided by the square root of the sample size. Okay, but before then, let's make this correction. 3.75 over 6, sorry, 3.75 over 6, I think the figure is 0.625, okay? And when you find the square root of 0.625, you get 0.791. So let's make this correction. Sorry about that. Now, the theory says that the standard deviation of this sample mean, which is this figure, okay? The standard deviation of these sample means, the standard deviation of these sample means, the sample means their mean is this, but their standard deviation is this. Okay, it should be equal to the population standard deviation divided by square root of the sample size. So remember that the population standard deviation was 1.118. Divided by the square root of the sample size. The sample size is 2. Okay, so 1 divided by 1.11 divided by square root of 2, you are going to get 0.7905 something, which is the same as 0.791. So we have proven the second theory. So the second theory is just saying that if we find the standard deviation of all sample means of a sample size of n, okay, that sample standard, the standard deviation of all sample means should be equal to the population standard deviation divided by square root of the sample size. We have also proven that. For further clarification, let's compute that for a sample size of 3. All right, remember, when we chose a sample size of 3, we had these figures. When we chose a sample size of 3, we have these figures. That was here. All right, so when we chose a sample size of 3, we had these figures. And their average was 2.5. Okay, their average was 2.5. So let's, as I said, let's try that. So for sample size of 3, these were the sample means. You already know it, so I'll not repeat myself. So there was 2.33, 3, and 2.67. Okay, and 2.67. These were the sample means of a sample size of 3. And when we find the mean of this sample mean, we had 2 plus 2.33 plus 3 plus 2.67 all over 4. So we had 10 over 4, which was 2.5, which was the same as the population mean. Now we are going to find the standard deviation of these sample means, okay, for a sample size of 3. So it will be 2 minus 2.5. squared plus 2.33 minus 2.5 squared plus 3 minus 2.5 squared plus 2.67 minus 2.5 squared all over 4. Okay. Now, if you compute this, we are going to get a certain standard deviation, and then you can use that standard deviation to also prove the formula. All right. To also prove this formula, you are supposed to get approximately the same answer. So we have proven the second theorem. Now let's go to the third theorem. So the third theorem says that if a population is normally distributed, so it means that the first and second theorem has to do with random sampling, if the samples were taken randomly. But the third theorem has to do with normal distribution. If a population is normally distributed with a mean of mu and a standard deviation of population standard deviation, the sampling distribution of the sample mean is also normally distributed. All right. So here, what it means is that from the theory, the sampling distribution of the sample mean is also normally distributed with the mean equal to population mean and a standard deviation equal to population standard deviation divided by the square root of the sample size. So all that this theory is saying is that what we have done in theory 1 and 2 is the same. So all that we are saying is that if the distribution is normal, the mean of all sample means is also normally distributed, all right? And then the standard deviation is equal to the population standard deviation divided by the square root of sample size. So in essence, what this theory is saying is that theory 1 and 2 will hold when the distribution is also normally distributed, all right? That is the simple way we can explain this. Now, another thing we must learn as we move along is what we call consistent estimator. Consistent estimator. Now we say that an estimator is consistent when the difference between the estimator and the parameter tends to become smaller as the sample size becomes larger. Okay. Now let's look at something. We are saying that population or the standard deviation, of the sample means is equal to population standard deviation divided by square root of sample size. So the standard deviation of the sample means, as we have proven, is equal to population standard deviation divided by square root of the sample size. All right. Now we all know that mathematically, as the n becomes larger, let's listen. As the n becomes larger, okay, as the n becomes larger, what is going to happen is that this whole fraction is going to become smaller, okay? What is going to happen is that this whole fraction is becoming smaller. And what it also means is that the standard deviation of the sample means is also becoming smaller. If this fraction is becoming smaller, this figure is also becoming smaller because this is equal to this. Now, the question we must ask ourselves is that what is the difference between a sample mean, all right? Let's show it. What is the difference between a sample mean and its average, which is the average of all sample means is the population mean, all right? So it means that if you want to look at how this figure or how these figures are spread about their average, it means that it is the standard deviation of these figures. So the standard deviation of these figures, that's what we had, 0.791. It means that on the average, all the sample means are far from their average. Okay, the sample means their average is population mean. So all the sample means are far from their average, which is the population mean, by this score. All right. So it means that the standard deviation of the sample means, it tells how the individual sample means are far from their average, which is the population mean. So we must know that as the sample size becomes larger, okay, the standard deviation of the sample means becomes smaller. As the sample size becomes larger, the standard deviation of the sample means become smaller. And if the standard deviation of the sample means is becoming smaller, what it means is that the sample means are getting close to their average, which is the population mean. All right. That is why we are saying that an unbiased estimator is said to be consistent when the difference between the estimator, which is probably the sample mean, and the parameter, which is the population mean, becomes smaller as the sample size becomes larger. All right. So this will bring us to the first part of my series of videos on sampling distribution. The next part, I'll be teaching on the Z-score, and then I'll also be teaching on the Z-scores, and I'll also be teaching on the fourth theorem, all right? I'll also be teaching on the fourth theorem, all right? So we'll meet in the next video.